Welcome dear learners. We are continuing quantum chemistry and in this module we are focusing on variation method for helium. The contents of this module include variation method, variation theorem, linear variation functions, helium atom problem a description, the Schrodinger wave equation for the helium atom, variation method for normal state of helium. First of all, variation method. As we know, there are two important approximation methods in quantum mechanics. These two important approximation methods are variation method and perturbation theory. The variation method, in particular the linear variation method, are the most widely used approximation techniques in quantum chemistry. This variation method is based on variation theorem. This method provides a simple way to place an upper bound on the ground state energy of any quantum system. This method uses trial wave functions. That means, in variation method, we must have a trial wave function to evaluate energy based on that trial wave function. And it should be noted that the calculated energy is always greater than the ground state energy of the system. That is the variation theorem, and the variation method is based on variation theorem. Now, consider the ground state of some arbitrary quantum mechanical system. The ground state wave function is denoted as psi0, and the ground state energy is marked as E0, and psi0 and E0 satisfy the Schrodinger wave equation Hamiltonian psi0 equal to E0 into psi0. For convenience, I mark it as equation number 1, and in order to illustrate the variation method, we have to left multiply this Schrodinger wave equation with the psi0 star and integrate over all space. This mathematical procedure is to evaluate the ground state energy of the system. So, we have to left multiply equation 1 with the psi0 star and integrate over all space. Therefore, equation 1 becomes integral psi0 star s hat psi0 d tau equal to E0 being a constant can be taken outside the integral sign, will be equal to E0 into integral psi0 star. This term came because we have left multiply with the psi0 star on both the sides of equation 1. Psi0 star psi0 d tau. This implies that we can calculate the ground state energy of the system from this equation itself. Therefore, E0 will be equal to integral psi0 star h hat psi0 d tau divided by integral psi0 star psi0 d tau. This will give the ground state energy of the quantum mechanical system, and this ground state energy is always less than the calculated energy using any trial wave function. In a similar way, we can calculate the energy which is above the ground state energy. For that, we have to take a trial wave function phi, which is an approximation. That is, the trial wave function is a function constructed to emulate the state psi0. The calculated energy would be E phi equal to integral phi star Hamiltonian phi d tau divided by integral phi star phi d tau. This integral can be replaced by using bracket notation in quantum mechanics. So, this equation can be represented also by using the bracket notation. This integral is termed as the variational integral. This integral or this ratio is also known as the variational integral. Here, the calculated energy is E phi. Note the point, E phi is the energy calculated based on purely a trial wave function, that is phi. So, the energy calculated based on phi is represented as E phi. Now, variation theorem provides the basis of variational method. This point I have already mentioned. The variation theorem states that any trial function other than true function psi 0 would give an energy E phi that is higher than true energy E 0, which implies that E phi greater than or equal to E 0. E phi is the calculated energy of the system using a trial wave function phi. That must be greater than or equal to ground state energy. The equality holds good if and only if the value of phi will be equal to psi 0. That means the calculated energy will always greater than ground state energy, but at a certain circumstance, if phi reaches psi 0, that means phi is equal to psi 0, then the value of E phi will be equal to E 0. Otherwise, the value of E phi will be greater than E 0. This is the implication of the variation theorem, and based on this theorem, the entire variation principle will proceed. Now, the variational principle says that we can calculate an upper bound to the ground state energy E 0 by using any trial wave function. The closer phi to psi 0, in some sense, the closer E phi to E 0. We can choose a trial wave function phi such that it depends on some arbitrary parameters. These arbitrary parameters alpha, beta and gamma are termed as variational parameters. This means the trial wave function depends on some variational parameters. For convenience, it is denoted as alpha, beta, gamma, etc. Now, the energy also depends on these variational parameters alpha, beta, gamma, etc. Hence, the calculated energy E phi can also be represented as a function of variational parameters, such that E phi of alpha, beta, gamma, etc. greater than or equal to E 0. This is the variation principle. Now, we have to perform one more step before arriving at the final result. This is the minimization of E phi, minimization of the calculated energy. Once energy is calculated by using variational integral, we have to minimize the calculated energy with respect to each of these variational parameters. And that minimization gives exact, nearly exact ground state energy E 0. So, first we have to calculate the energy of the system using a trial wave function that is marked as E phi, and the E phi has to be minimized with respect to variational parameters. And by using that minimum energy, we can interpret the result. That minimum energy will be more close to ground state energy of the system. Now, linear variation functions. This is another important aspect of variational principle or variation principle. In variation method, a trial wave function will be constructed with adjustable parameters so that it could be varied to improve the trial wave function. If a trial wave function phi is represented as a linear combination of some arbitrary functions, then the trial function phi is known as the linear variation function. That is, phi can be represented as a linear combination. If a trial wave function phi is as a linear variation function, then we can write phi is equal to summation from n is equal to 1 to capital N Cn Fn. Here Cn are known as the variational parameters and Fn are arbitrary known functions, and such arbitrary known functions at least satisfy the boundary conditions. Now we are moving on to the helium atom problem, and prior to apply variational principle to the helium atom problem, we have to discuss the basic aspect of the helium atom problem. So, we are providing a description of the helium atom problem. The helium atom problem is a 3-body problem or a 3-particle problem. Definitely, it comprised of 2 electrons and a nucleus. The charge of the nucleus is plus 2e because it contains 2 protons. We shall consider the nucleus to be at rest and place the origin of the coordinate of the system at the center of the nucleus. The coordinates of the electron 1 and 2 are simply marked as x1, y1, z1 for the first electron and x2, y2, z2 for the second electron. Now, This is the pictorial representation of the three particle problem, that is our helium atom problem. This portion represents electron, and this is the place of the second electron, and the distance of the second electron from the nucleus is taken as R2. This is electron number 1. Distance of the electron from the center of the nucleus is marked as R1, and finally R12 represents distance between two electrons of the system under consideration. As I mentioned, R1 and R2 are the distance of the electrons 1 and 2 from the nucleus. R12 is the distance of the electron from 1 to 2, and Me represents the rest mass of the electron. We are familiar with the rest mass of the electron. Rest mass of the electron is 9.1 into 10 raised to minus 31 kilogram. This about the representation of the helium atom problem. Now we have to discuss the Hamiltonian operator of the helium atom problem. The Hamiltonian operator S hat of a helium atom can be simply represented like this. S hat is equal to minus S cross square by 2me into del 1 square plus del 2 square minus 2e square by 4 pi epsilon 0 into 1 by r1 plus 1 by r2 plus e square by 4 pi epsilon 0 into 1 by r12. We are familiar with all the terms that appeared in this equation. Del 1 square and del 2 square represents the Laplacian operator corresponds to the position of the first and second electrons. R1 is the distance of the electron first from the nucleus. R2 is distance of the second electron from the nucleus, and finally R12 is the distance between two electrons of the helium atom problem under our consideration. Now, this Hamiltonian operator contains different parameters, different parts. The first term is the operator for the electron's kinetic energy, which simply means that minus S cross square by 2me into del 1 square plus del 2 square part, this first term of this Hamiltonian operator corresponds to the kinetic energy of the system. We know the fact that Hamiltonian operator S hat is the total energy operator. It comprised of two parts, the kinetic energy as well as the potential energy. So, in this Hamiltonian operator for the helium atom problem, the first portion, the first term represents the operator part corresponds to kinetic energy. The second term that is minus 2e square by 4 pi epsilon 0 into 1 by r1 plus 1 by r2 represents the potential energy term of attraction between electrons and the nucleus. We know the fact that electrons being negatively charged is under attractive force with the positively charged nucleus. Such a kind of attractive potential energy term is included in the second term of the Hamiltonian operator. Finally, there is one more term, that is e square divided by 4 pi epsilon 0 into 1 by r12. The last term is the potential energy of inter-electronic repulsion. The last term represents potential energy of inter-electronic repulsion. So, finally, once again the concept is like this. The first term represents kinetic energy. The second term represents potential energy belongs to attractive force, and the final term represents the potential energy that arises due to inter-electronic repulsion. That all about the description of the Hamiltonian operator of the helium atom problem. Now, we have to consider the Schrodinger wave equation for the helium atom problem. We know Hamiltonian psi is equal to energy into psi, and we previously learned the value of the Hamiltonian operator, and we have to operate it with the state function of the system to get the Schrodinger equation, and this is the Schrodinger wave equation, the complete Schrodinger wave equation for the helium atom problem. And this equation is minus S cross square by 2me del 1 square plus del 2 square into psi r1 r2. Psi r1 r2 means the psi depends on r1 as well as r2. Therefore, I put psi r1 r2 minus 2e square by 4 pi epsilon 0 into 1 by r1 plus 1 by r2 into psi r1 r2 plus E square by 4 pi epsilon 0 into modulus of R1 minus R2 into psi R1 R2 should be equal to energy into psi R1 R2. This about the entire Schrodinger wave equation for the helium atom problem. The Schrodinger equation cannot be solved exactly for the system. This is because of the existence of the last term. The last term, that is this third term on the left hand side, comprised of some potential energy that arises due to interelectronic repulsion, and that offers some hindrance to get exact solution to this Schrodinger wave equation. Therefore, we have to resort to some approximation methods to solve this Schrodinger wave equation, and in the present situation we are taking variation method as the approximation method to solve the Schrodinger equation for the helium atom problem. Moving on to variation method for helium atom. We can use the variational method to estimate the ground state energy of a helium atom by keeping the fact that the calculated energy, even though it is calculated as ground state energy, that must be greater than the actual ground state energy of the system. That is variational principle. The Hamiltonian operator for helium atom problem we already learned, that is S cross square is equal to minus S hat is equal to minus S cross square by 2m E del 1 square plus del 2 square minus 2 E square by 4 pi epsilon 0 into 1 by R1 plus 1 by R2 plus E square by 4 pi epsilon 0 into 1 by R12. Here the epsilon 0 term is the permittivity factor, and this equation can be written in a more simplified form like this, that is S hat equal to S hat H1 plus S hat S2 plus E square by 4 pi epsilon 0 into 1 by R12, and I mark it as equation number 2, where S hat Sj is equal to minus S cross square by 2m E del j square minus 2 E square by 4 pi epsilon 0 into 1 by Rj. That is marked as equation number 3, where j is equal to 1 and 2 corresponds to 2 electrons, electron first and electron 2 in helium atom problem, and the Hamiltonian operator around the helium nucleus is H hat Hj. Thus, H hat H1 for first electron and H hat H2 for second electron satisfy this equation H hat Hj psi H Rj theta j phi j, where psi j Rj theta j phi j represents the wave function corresponds to jth electron in spherical polar coordinate, and that must be equal to Ej psi j Rj theta j phi j. J may be 1 or 2. If I can put j is equal to 1, then H hat H1 equal to psi h R1 theta 1 phi 1, and RHS will be E1 psi h R1 theta 1 phi 1. Similarly, I can put j as 2 also to get the corresponding Hamiltonian operator for the second electron. Now, Ej H hat Rj phi j theta j is a hydrogen-like wave function, but for the helium atom problem, Z is equal to 2, and Ej can be calculated by using this expression. Ej energy of the system, Ej, j may be 1 or 2. If j is equal to 1, we can calculate the energy of the first electron. If j is equal to 2, we will get energy of the second electron. The general expression is like this: Ej equal to is minus z square me e raised to 4 divided by 32 pi square epsilon 0 square s cross square n j square. This is the general expression for getting the energy of the system. And in this expression, if we ignore the interelectronic repulsion term, then the Hamiltonian operator is separable. That is, you can separate the Hamiltonian operator. In the presence of the interelectronic repulsion term, the separation is not possible. Therefore, for convenience, we are ignoring the interelectronic repulsion term, and we have to separate the Hamiltonian operator. The ground state wave function would be phi 0 R12. This is a ground state trial wave function, and let it be marked as psi 1 as R1, psi 1 as R2, where psi 1 as R1 and psi 1 as R2 are two arbitrary wave functions. And here psi 1 as Rj equal to Z cube by pi a0 the whole raised to 1 by 2 e raised to minus Z Rj by a0, where j is equal to 1 or 2, since the helium atom problem consists of 2 electrons. And we can use this equation, equation 6 and 7 to set out a trial wave function, and in that trial wave function Z is a variational parameter or variational constant. Now, we have to evaluate the variational integral to get the ground state energy of the system based on the trial wave function. And for that, we have to evaluate this integral. That is Ez is equal to integral phi 0 r1 r2 h hat phi 0 r1 r2 dr1 dr2. This is the numerator part of the variational integral, and also we know h hat that is splitted into several parts, h hat 1, h hat 2 plus e square by 4 pi epsilon 0 into 1 by r onto. On evaluation, we will get the energy of the system, and this energy is purely evaluated based on the variational theorem and variational integral, and the calculated energy Ez equal to Z square minus 27 by 8 into Z. This is the calculated energy of the system. Here the energy should be in unit of atomic units, that is me into e raised to 4 divided by 16 pi square epsilon 0 square s cross square, where s cross equal to h by 2 pi, me represents mass of electron, e represents charge of electron, that is equal to 1.602 into 10 raised to minus 19 coulombs, 16 is a constant, pi is equal to 3.14, that is again a constant, and here energy part, this Ez is in terms of this unit, me e raised to 4 by 16 pi square epsilon square s cross square. And we got this energy value, and as a procedure in the variation method, we have to do some more calculation parts. That is, we got this energy based on a trial wave function we selected, and this energy to be minimized with respect to the trial wave function Z. And in the present problem, we take the fact that Z is taken as the variational parameter. So, using this variational parameter Z, we have to minimize this calculated energy. As a condition for minimization with respect to each and every variational parameter, the first part we have to perform is differentiate this expression with respect to variational parameter and put the first differential equal to 0. Then we will get an equation. From that equation, we can calculate the variational parameter. By putting that variational parameter again into original energy equation, we will get the minimized energy, and that minimized energy to be compared with the ground state energy of the system. Then we will get an idea that the variation principle is correct and calculated energy will always be greater than the ground state energy of the system. And in order to illustrate the minimization part, we are performing to differentiate this energy expression with respect to Z first, by keeping the fact that in this energy expression, Z is taken as the variational parameter. As a procedure for minimization, we have to differentiate this equation. So, I am going to differentiate this equation 9 with respect to Z. On differentiation, I will get dou E Z divided by dou Z equal to first differential of Z square, that is dou by dou Z of Z square. We know that result is equal to 2Z, that is differential of Z square is equal to 2Z minus 27 by 80 can be taken as a constant into dz by dz, that is equal to unity. Therefore, 27 divided by 8 into 1, and this can be taken as 0. This is the condition for minimization. Since dou Z by dou Z is equal to 2Z minus 27 by 8 is equal to 0, we can put 2Z by 2Z equal to 27 by 8. Therefore, the value of Z, I can take that value as Z minimum. Since Z minimum representation is because of the fact that we are minimizing this energy with respect to Z. The corresponding value of Z is taken as Z minimum. Therefore, Z minimum is equal to, you can cross multiply 2 to the denominator, Therefore, I will get 27 by 16. This is the value of Z minimum. This already I got. Z minimum is equal to 27 by 16. And now to get the minimized energy, we have to substitute the value of Z minimum in the original energy expression. Therefore, I will get energy minimum. Energy minimum equal to Z square. Z square should be replaced by Z minimum square. Z minimum is equal to 27 by 16. So, 27 by 16 the whole square minus 27 by 8 into value of Z minimum. Z must be replaced as Z minimum, then Ez is changed to E minimum. So, 27 by 8 into Z minimum. Z minimum is 27 by 16. For convenience, I can take 27 by 16 as a common factor. Therefore, E minimum, energy minimum will be equal to 27 by 16 into the first term again a 27 by 16 minus 27 by 8. 27 by 8. So, this part will be minus 27 by 6. The term inside the bracket is minus 27 by 6. Minus 27 by 6 multiplied by 27 by 6. So, I got energy minimum equal to minus 27 by 16 the whole square. 27 by 16 the whole square. This is the value of energy minimum. Thus, energy minimum equal to 27 by 16 the whole square. That can further be simplified as, in terms of atomic unit, we will get it as minus 2.8477 in atomic units. That is, energy minimum of the system will be, for helium atom problem will be minus 2.8477 atomic units. This about the calculated minimized energy of helium atom based on a trial wave function phi. Now, the value of E minimum, the calculated value minus 2.8477, that is in good agreement with the experimental result of minus 2.9033. Minus 2.8477 is always greater than this actual experimental value. That is the basic principle of the variational theorem. So, we achieve a fairly good result considering the simplicity of the trial wave function. That means, the calculated value, the minimized energy value minus 2.8477 is higher than the experimental value, and these two values are very close to each other, and this implies that the wave function we selected, that is the trial wave function, is a good result or a simple wave function that give accurate, more or less accurate result for the helium atom problem. The value of Ez, that to minimize Ez, can be interpreted as an effective nuclear charge. The fact that Ez comes out to be less than 2 reflects that each electron partially screens the nucleus from each other, That is, the value of Z, theoretically, the nucleus consists of 2 protons. Therefore, we are anticipating the value of the nuclear charge to be 2 plus 2. But the calculated result is 27 by 16, that is less than 2. Here there is a decrease is observed. This decrease is due to the decrease in effective nuclear charge, and 27 by 16 is taken as the effective nuclear charge. Hence, the net effective nuclear charge is reduced from 2 to 27 by 16. And note that the value 27 by 16 is less than 2. This effect is due to some screening effect of the second electron offered to the first electron. And screening effect causes the diminishing of actual nuclear charge to 27 by 16. Thus, in this discussion, we have mentioned the variation method for helium atom and we illustrated the variation method for helium atom by selecting a trial wave function. We calculated the energy, we minimized the energy and interpret the result. That all about the present module. Thank you.